When upgrading an electrical branch circuit for a commercial application, there are several key considerations. This discussion reviews the design choices involved in such an upgrade. Firstly, consider the use of parallel conductors in conduit. It's acceptable to install both parallel circuits in the same conduit. Secondly, sizing the conductors. The calculations for conductor ampacity and sizing are crucial and should be accurate. The use of 600 ohm CMTHHN copper conductors is appropriate for the specified load requirements. Thirdly, overcurrent protection, or OCP selection. The decision between a 600 amp or 800 amp breaker for the motor control center, or MCC, depends on the anticipated inrush current. If specific information from the equipment manufacturer is unavailable, a breaker rated for 6 to 8 times the full load current is generally recommended. In the example, an 800 amp breaker might be necessary. Consulting with the manufacturer or an experienced electrician is advisable in this case. Fourthly, consider the fuse disconnect selection. Similar to the breaker selection, choosing between a 600 amp or 800 amp fuse disconnect hinges on the anticipated inrush current. A 600 amp fuse disconnect may be suitable if the inrush current is expected to remain within the 6 to 8 times the full load current range. Fifthly, voltage drop. The voltage drop calculations must be performed correctly to ensure an acceptable percentage drop, ideally less than 3%. Sixthly, using a splice box. Installing a splice box is acceptable when dealing with excessive bends in a conduit run. Ensure that the splice box complies with applicable codes and meets the manufacturer's specifications. Now, addressing concerns about conductor quantity. While the number of conductors might seem excessive, it is often necessary to ensure proper ampacity and to account for dirting. To address the inrush current consideration, confirming the anticipated inrush current with the equipment manufacturer or through testing is very important. This information is crucial for determining the appropriate overcurrent protection settings. Some additional considerations include grounding and insulation. The equipment should be properly grounded according to the relevant electrical codes. All conductors and equipment should be installed in accordance with industry standards and local building codes. It is important to keep thorough documentation. Maintain a record of all design calculations, assumptions, and any deviations from the original design. As a general overview, the design should meet the requirements for the project. However, it is always a good practice to have the design reviewed by a qualified electrician or engineer for verification. The National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety and compliance. Several articles and tables within the NEC are relevant to this design. Article 310.4 addresses the use of conductors in parallel, specifying conditions under which conductors of size 1/0 AWG and larger can be run in parallel. This section emphasizes that all parallel conductors must be the same length, conductor material, circular mill area, insulation type, and be terminated in the same manner. Table 310.15b2 provides the adjustment factors for the number of current-carrying conductors in a raceway or cable. When multiple conductors are installed in close proximity, their ampacity must be derated to prevent overheating. For example, with 6 current-carrying conductors, an 80% dirting factor applies. Table 310.16 lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in various conditions. This table is used to determine the appropriate conductor size based on its ampacity and temperature rating. Annex C, specifically Table C 1A, provides information on conduit fill, indicating the maximum number of conductors of a given size that can be installed in a particular size of conduit. This table is essential for ensuring that the conduit is not overfilled, which can lead to overheating and damage to the conductors. Section 240.4c addresses the protection of conductors against overcurrent. This section allows for the next highest standard overcurrent device rating to be used in certain situations, such as when the calculated ampacity does not correspond to a standard breaker size. However, it's important to ensure that the overcurrent device does not exceed the conductor's ampacity. Article 430 covers the requirements for motor circuits, including overcurrent protection, disconnecting means, and motor controllers. This article is particularly relevant when dealing with motor loads and variable speed drives. Section 250.122 specifies the requirements for equipment grounding conductors, including the minimum size of the grounding conductor base and the size of the overcurrent protective device. When using parallel conductors, the grounding conductor must be sized accordingly. Article 300 provides general requirements for wiring methods and materials, including conduit installations, conductor identification, and protection against physical damage. This article covers various aspects of electrical installations to ensure safety and reliability. Voltage drop is an important factor to consider when designing electrical circuits, especially for long runs. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The formula for calculating voltage drop in a three-phase circuit is voltage drop equals to *k**L** I* 0.866/cm, where K is the conductor's resistance per circular millifoot, L is the length of the conductor in feet, I is the current in amps, and cm is the circular mil area of the conductor. The NEC recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. To mitigate voltage drop, larger conductors can be used, or the circuit can be divided into multiple smaller circuits. When installing conductors and conduit, it's important to follow the manufacturer's recommendations and the NEC guidelines for conduit fill. Overfilling the conduit can make it difficult to pull the conductors, damage the insulation, and reduce the conductor's ampacity due to poor heat dissipation. The NEC specifies the maximum number of conductors allowed in a conduit based on the conduit size and the conductor's dimensions. When making splices in a splice box, it's important to use connectors that are listed and labeled for the application. The connectors must be properly sized for the conductors being spliced and installed according to the manufacturer's instructions. The splice box must be large enough to accommodate the connectors and the conductors without overcrowding. Grounding is a critical aspect of electrical safety. The equipment grounding conductor provides a low impedance path for fault current to return to the source, tripping the overcurrent protective device and energizing the circuit. The grounding conductor must be properly sized and connected to all metal enclosures and equipment to ensure effective grounding. Overcurrent protection is designed to protect conductors and equipment from overloads and short circuits. Overcurrent protective devices, such as circuit breakers and fuses, interrupt the flow of current when it exceeds a predetermined level. The overcurrent protective device must be sized to protect the conductors and equipment it serves, but it should not be so large that it allows excessive current to flow during an overload. When selecting conductors for an electrical installation, it's important to consider the conductor's insulation type, temperature rating, and ampacity. THHN conductors are commonly used in commercial and industrial applications due to their high temperature rating and resistance to moisture and abrasion. The conductor's ampacity must be sufficient to carry the load current without exceeding the conductor's temperature rating. When dealing with variable speed drives, or VSDs, it's important to consider the harmonic currents that they generate. Harmonic currents can cause overheating of conductors and equipment, as well as interference with other electronic devices. To mitigate harmonic currents, filters or reactors can be installed to reduce their amplitude. In addition to the NEC, local built-in codes and regulations may also apply to electrical installations. It's important to consult with local authorities to ensure that the installation complies with all applicable codes and regulations. A thorough understanding of electrical principles and practices is essential for designing and installing safe and reliable electrical systems. Continuing education and training can help electricians and engineers stay up to date on the latest codes and technologies. For a 480-volt three-phase system, the voltage between any two phases is 480 volts, and the voltage from any phase to ground is approximately 277 volts. This voltage level is commonly used in commercial and industrial applications for powering motors, lighting, and other equipment. When working with electrical systems, it's important to use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. Electrical work can be dangerous, and PPE can help to protect against electric shock, burns, and other injuries. A qualified electrician should always perform electrical work, as they have the knowledge, skills, and experience necessary to do the job safely and correctly. Attempting to perform electrical work without proper training can be dangerous and may violate local codes and regulations. Regular inspection and maintenance of electrical systems can help to prevent problems and ensure safe and reliable operation. Inspections should be performed by a qualified electrician and should include checking for loose connections, damaged insulation, and other potential hazards. The National Fire Protection Association, or NFPA, publishes a variety of codes and standards related to electrical safety, including the NEC and NFPA 70E, which covers electrical safety in the workplace. These codes and standards provide guidance on safe electrical practices and are widely used in the electrical industry. When designing an electrical system, it's important to consider the future needs of the facility. The system should be designed to accommodate future expansion and changes in load requirements. This may involve installing larger conductors and equipment than are currently needed or providing space for future additions. In addition to the technical aspects of electrical design, it's also important to consider the economic aspects. The cost of materials, labor, and energy should be factored into the design process. A well-designed electrical system can save money on energy costs and reduce the risk of equipment failure. The use of energy-efficient lighting, motors, and other equipment can significantly reduce energy consumption and lower operating costs. Energy-efficient equipment may also qualify for rebates or tax incentives, further reducing the cost of the installation. Proper wiring and termination techniques are essential for ensuring reliable electrical connections. Loose or corroded connections can cause overheating, voltage drop, and equipment failure. All connections should be made using appropriate connectors and tools and should be towed to the manufacturer's specifications. Labeling of electrical equipment and circuits is important for safety and maintenance. All circuits should be clearly labeled with their voltage, amperage, and the equipment they serve. This helps to prevent accidental contact with live circuits and makes it easier to troubleshoot problems. Documentation of electrical systems is essential for future reference and maintenance. Documentation should include wiring diagrams, panel schedules, equipment specifications, and any other relevant information. This documentation should be kept in a safe place and readily accessible to qualified personnel. The use of technology can improve the efficiency and accuracy of electrical design. Computer-aided design, or CAD, software can be used to create detailed wiring diagrams and panel layouts. Electrical calculation software can be used to perform load calculations, voltage drop calculations, and other electrical calculations. The NEC is updated every 3 years to reflect changes in technology and industry practices. It's important to stay up to date on the latest NEC requirements to ensure that electrical installations are safe and compliant. The authority having jurisdiction, or OJ, is responsible for enforcing the NEC and other local codes and regulations. The AHA may be a local building inspector, fire marshal, or other government official. It's important to work with the AHA to ensure that electrical installations meet all applicable requirements. Electrical safety is a shared responsibility. Electricians, engineers, contractors, and building owners all have a role to play in ensuring that electrical systems are safe and reliable. By following safe electrical practices and staying up to date on the latest codes and technologies, we can all help to prevent electrical accidents and injuries. When working with existing electrical systems, it's important to identify and address any existing hazards. This may involve correcting code violations, replacing damaged equipment, or upgrading the system to meet current standards. A thorough inspection of the existing system is essential before beginning any work. In addition to the NEC, there are other industry standards and guidelines that may be relevant to electrical installations. These standards may cover topics such as grounding, bonding, surge protection, and lightning protection. It's important to be familiar with these standards and to follow them when applicable. Coordination studies are used to determine the proper settings for overcurrent protective devices to ensure that they trip in a coordinated manner. This helps to minimize the extent of an outage and to protect equipment from damage. Coordination studies should be performed by a qualified engineer. Arc flash studies are used to determine the potential arc flash hazard at various points in an electrical system. This information is used to select appropriate personal protective equipment and to develop safe work practices. Arc flash studies should be performed by a qualified engineer. Power quality is an important consideration for many electrical systems. Poor power quality can cause equipment to malfunction, overheat, and fail prematurely. Power quality problems can be caused by harmonics, voltage sags, voltage swells, and other disturbances. Power quality monitoring equipment can be used to identify and diagnose power quality problems. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning, switching transients, and other disturbances. SPD should be installed at the service entrance and at downstream locations to provide comprehensive surge protection. Lightning protection systems are used to protect buildings and equipment from lightning strikes. Lightning protection systems consist of air terminals, conductors, and grounding electrodes. These systems provide a path for lightning current to flow safely to ground, preventing damage to the building and its contents. Ground fault circuit interrupters, or GFCIs, are used to protect people from electric shock. GFCIs detect ground faults and interrupt the flow of current before a person can be injured. GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, are used to protect against fires caused by arcing faults. RFCIs detect arcing faults and interrupt the flow of current before a fire can start. RFCIs are required in bedrooms and other areas where fire hazards are present. Emergency power systems are used to provide power to essential loads during a power outage. Emergency power systems may consist of generators, batteries, or uninterruptible power supplies, or UPSs. Emergency power systems are required in hospitals, fire stations, and other critical facilities. Renewable energy systems, such as solar photovoltaic systems and wind turbine systems, are becoming increasingly common. These systems generate electricity from renewable sources and can help to reduce reliance on fossil fuels. Renewable energy systems must be designed and installed in accordance with the NEC and other applicable codes and standards.